Hi friends, as you are watching this video, I believe you know what is CodeAbbey, and you know that recently you have found that recently there came problems in the language scheme. One of the first problem is introduced in this language, and I'm going in this video, which will appear instead of this image, briefly in 10 to 15 minutes to explain you how to write basic things in it so that you can start immediately. The language is simple, so it's quite possible. There is a small preface about how old it is, about its being a dialect of Lisp language, and here is the link to more detailed instructions, and here you may find that we are using tiny scheme interpreter, very small interpreter in single C file, which is run on our server. So you submit a solution and it could be checked against some hidden input, etc. Now, if you click here, you find there a web page for this tiny scheme. It's really our own variant of it, slightly improved to recent standard. And here are links to sources if you want to hack them, to downloads where you can take a scheme exam, for example, in the Windows bundle. I believe you then want to download this tiny scheme win. And for Linux and OS X, you shall simply make link your own executable, and then there is an in-browser emulator which we can use as a sandbox, and where I'm going to show you further things. We are going to cover several topics: basic operations, then setting variables. Hopefully I pronounce this word right. Then data types, other data types, then lists and pairs as a complex data types, and then function definitions and loops. That would be enough. Now let us start with these basic operations. You see I type into this input box. Now I type it as a command. When I click execute button or press Ctrl Enter, things are executed, evaluated, and printed here in the upper part. Let us try something. Let us try to use these words, basic operations, as a string in quotes, and press Ctrl Enter. It's evaluated, and we found that it is string with the words basic operations. Wonderful. Instead of hello world, right? If we try to evaluate some integer, some number, we also see it just evaluates to itself, just as in Python interpreter, for example. Now we usually want to do some operations, like a couple of values. In scheme, this happens slightly different. All operations are written first in surrounded in parentheses, and then there are written operands like this: plus 5, 3. It's 8, so it works. And what is good about this notation, which is called prefix notation, is that we can really put many values within a single operation, right? And it's also easier to parse for interpreter. Okay, this works. What is a usual seen as a slight disadvantage is that it's slightly not very something to which we are acquainted. So if we want some complex expression like sum 5 plus 3 and multiply it by the difference between 7 and 2, for example, like this, how it is written in scheme. The outer operation is multiplication, and it is done over two sub-expressions. One of them is plus 5 3 and another is minus 7 2, right? Let's try it. It works. There are also some functions to which we get used to. For example, square root, sqrt, sqrt of 2, for example, well-known value 1.4. We even can try to write down complex expression on example of Pythagorean triangle, or it's also called Egyptian, I believe. The triangle with the two sides of 3 and 4, and we want to get its right triangle, and we want to get its third side. We need to take square root of the sum of two multiplications of 3 by 3. It's one side squared, and 4 by 4. It's another side squared, right? Okay, we also can even write this into several lines. For example, here it comes with some indentation, right? Even like this. You see, it's good to have an editor which highlights parentheses, matching parentheses, so we never forget them. Okay, Control Enter, and we know that the third side is 5. Now we are going to go further to variables, right? They are defined with the word define. Define name of variable, for example, x, and some value, for example, 3. Now it shows it's defined, and if we call it, it yields 3. Names could consist of something more than just letters. For example, my favorite string variable, right? For example, yeah, it works, but I won't repeat it. Now they also could be redefined, and they could be set to different value. These are slightly different things, though they behave quite similarly. If, for example, I define x to 5 now, x becomes 5. But I can do also set x different value, right? And now it is 13. Okay. You may notice that set is written with an exclamation mark in the end. Things which change something in variables are functions which mutate variables. They are written with exclamation mark by agreement. Now we can do operations on variables as on literal numbers. For example, multiply x by x, it works. And there are also useful functions to check the type of the value in the variable. For example, the function number, you see it ends in exclamation mark, and it says true. That's the way to say true, and the way to say false is f. For example, if we define y to some string like this, and try to check whether it is number, we surely get false. Besides checking for number, there are checks for example, strings. Is string for y, for example, it's true, no wonder. There are also different types, but probably we cover this a bit later when we start speaking of types and lists. So let's speak of types, and as usually there are some simple types and some complex types. Let me enumerate them. How to do this? Simple types are numbers, strings, which we already have seen, and Boolean values. We also seen them as a result of operations which give true or false. There are also symbols and characters or chars as elements of string, but probably we shall not discuss the last two now. You won't immediately need them. As about others, there are of course complex types, and there are not many of them. At some point scheme get vectors, which we call arrays in some other languages, but this was later. But originally all we had were lists, or rather pairs. We shall look how useful and universal these data containers are. So let's recap. We know there are numbers, integers, and not integers, values with floating point, really. There are some ways to distinguish them, to convert them, but generally they are interchangeable. And more advanced versions of Scheme and Lisp, they also use complex numbers and fractions, but in Tiny Scheme this seems to be unnecessary, so there are no such things. And as about strings, they are just text enclosed in quotes, and that's all. As about Boolean, it has two values, true and false, just as letters T and F are prepended with a hash symbol, and they are results of various logical operations. For example, 50 is greater than 30, true, and there are things like and, 50 greater than 30, and say, for example, is number value res 1. These prefixes become variables emulator also. You see there are functions and, or, etc. And surely there is an operation called if, which allows to calculate some expression. For example, is greater as 1 than 0. And if so, it executes a first expression after this, which was checked. Let us write it in separate line. Let it be display yes, and otherwise display no. As you may guess, display simply prints a thing into output, and let us see how this works. This prints yes. You see the result of function is anyway also shown as true, and it is shown in the same line because display doesn't add new line. Usually if you want to print several things, you need to write either something like this. Begin, despite its name, allows simply to block several expressions together. So it could be begin and then display value is, then display value itself, for example 13, and then print new line. It seems to be verbose again, but there is simply way to do this. You probably may learn this later. Okay, this all was about simple data types. I said there are few more, but it's not important now. Let's go to complex types, and of them we won't cover vectors right now, but we concentrate on lists and pairs. A list is created of values with the call to function list. Surprisingly, 10, 20, 30, 40, for example, and for example, here could be hair among of numbers. You see, list is heterogeneous and can contain values of different types. Let us assign this list to some variable. For example, define my list. Okay, it's already in variable res10, but let us have something more memorable. My list, right? It prints my list. One of the obvious operation is a lookup by index in the list. It is called list reference, right? Then the list itself or variable pointing to it, my list, and for example, we want to extract hair, and so it's by index 2. Yeah, it says it's hair. Meanwhile, list of course wasn't changed. So it looks good, but it's not really as it looks, because really there is a function to check that something is list. For example, is list my list? Sure, but there is really a thing called pair, and it is built with, it's a pair of values, but it's built with a function named cons, not pair, for some reason, historical reason. For example, 13 and 21, for example. I shouldn't put any comma here, of course, no commas in scheme. You see, pair is depicted as two values separated by dot, and there is left and right part, and they are enclosed in parentheses. there are functions to get left and right part of the pair. Surprisingly, they are called car. For example, car of res 16 is 13, and another is for car is for left, and CDR is for right part of the pair. For example, res 16 again, it's 21. What is very interesting about this, these names, car and CDR, they are for legacy reasons. They are names of some register in some machine on which scheme Lisp was firstly implemented. But now let us ask, is pair, for example, res 16? Of course, this is clear. But is pair my list? Surprisingly too. But if it is a pair, then it should have a left and right part, right? Let us see what they are. Left part, car of my list, is its first value. Very interesting, right? But what is CDR then? It is a remainder of the list, and it's also very interesting. So list is really pair of first element and another list which gives the tail of the list. So really it consists of several pairs, several constants like this, 10 and another cons, right? 12, 20, and yet another cons, for example, 50, let it be. And now we need empty list somewhere. Empty list is described like this. The parenthesis prefixed by single quote. Let us execute it. You see it's a list of 3 values. So these pairs allows us to build lists, build trees of various configurations. So they are very powerful, but probably not the very fast data structure. Still, they are quite widely used. We can check, apply various functions to list. For example, calculate the length of my list, for example, right? But you now may guess that length should iterate through the whole list to figure out what is length is, and that's true. That is how it works. So now we are going to speak about the last thing, about defining functions and making loops. Defining functions looks very close to defining variables, like this. Define, just the same. Name is enclosed in parentheses, my func, for example, and some body, not somebody, but some body of a function, one or more statements. For example, display hello world. No, I don't like this. Hi people. And let us have also the line here. Okay, it shows the my func is defined. If I type it enter as I do with variables, you see it says something incomprehensible. Something is defined, but we don't understand what to do with it. To call the function, we need to give its name in parentheses as usually. If it has no arguments, we do not pass anything, but parentheses should be. Okay, it says hi people, and it even returns something. Now what is returned is really the value of the last expression in the body. For example, let us define function which calculates a square of a number, a square of x. For example, we just need to multiply x by x, right? Well, so far so good. Let us try it. SQR of 13, right? Exactly. This works, and we can surely use one definitions inside others. For example, let us define a hypot function found in some languages, which calculates hypotenuse of a right triangle with sides of given lengths, like this. Hypot x, y, and it should be just square root of sum of square of x and square of y. You see, luckily this auto completes parentheses for me, so I do not miss anything. We can execute this. And for example, a hypot of 5 and 12 is 13. Right, this works. And now let us try something more complicated. Let us try to define function which prints squares, for example. Let us call it prn sqr, starting from some number and ending at some different number. Start and finish arguments for this, and this is going to be a bit complicated because we do not know how many times to print, right? But let us do things in steps. First of all, we want to print the square of the start. Display sqr of start. Good. Let us add new line. Great. Perhaps we may add the start number itself, but it's not important. Now we want to print the remaining numbers, but we do not want to repeat ourselves. We just want this function to repeat itself. So we want really to call it prn sqr with the same finish, but with the start increased by 1 plus 1 start. This should work, but we almost forget one thing. We do not want to continue this endlessly. We need to stop when start reaches finish. So let us execute this last statement only if less than start is less than finish, right? Well, this should work. I will add this line here. There are some lack of parentheses, I believe. This should be correct. So once again, let's recap. We define function, starting and ending values, display whatever we want, and then we recursively call itself, but only if stop condition isn't reached yet. Let's try. It's defined. Let's try to call it from 5 to 15, for example. Great. You see it prints something and it returns something. About recursion, if we come from languages like C and Java and Python, we may feel that it may blow up our stack if there are too many iterations, but it's not the case with Scheme, because when it is what we call tail call optimization. If some function does the call to itself, which do not require to do anything after it, then it's really transposed into a simple loop inside the interpreter. So it may work endlessly without touching stack itself. That's all about functions, I believe, and at this point you are ready to continue with the problems. I recommend you to download, as I have shown, download either bundle for Windows with the ready executable inside, or sources and run make or GCC over them in Linux or OS X site. You may also recollect there are links to some additional materials. Structure and Interpreting of Computer Programs is a classic book about scheme and about programming itself. There are standards on the languages with a list of useful functions, and there is just central resource for the language with the other interpreters, with the standards, etc. So good luck. Thank you for watching so far.